Okay, good. So let's restart it here, right? So I can repeat. So today is February 15, 2023, and today we're going to do our first lab, electric field 1 uniform field lab. Okay, electric field 2 is not going to be the uniform field. It's going to be a different type of field, okay? And I'm going to tell you exactly what the uniform field means. In this lab, we are going to use two concepts. This concept of the electric field, one, that we already covered, and two, the concept of electric potential, which I'm going to cover quickly right now, and then we're going to go into more detail in the lecture. Okay, so we have the idea of force. We have the idea of field. You have seen that in mechanics already, in physics 6. And even the potential energy, you also saw that in mechanics. Okay, it just happened here that in mechanics, we didn't call it a field, we call it an acceleration of gravity. Okay, so here you go. I'm going to separate those two forces, right? We have the gravitational force, we have the electrical force. For the case of the field, we have the acceleration of gravity, which is the gravitational force divided by m. Acceleration of gravity again has another name that we call gravitational field. And we also have the electrical field, which is nothing more as the force, the electrical force, divided by the source of the electric field. Here is gravitational force divided by the source of the gravitational field. Okay. And then what did you see as well in mechanics? What else do we see? Okay, can you? I want to make sure that you can see this screen. Okay, I'm going to move it up and down. Can you see it? Just confirm that with me that you can see it.
Yeah, we can see it.
Okay, yeah. But I have two screens here, and sometimes I get confused which screen I'm showing. So I'm showing the correct screen. Thank you. So in the case of the potential energy, right? We can have the gravitational energy, the gravitational potential energy. And we can have also, the electrical potential energy that I didn't introduce to you yet. We're going to introduce that right now. Finally, we can also define something called the gravitational potential. Okay, remember, there is gravitational potential energy, and then there is gravitational potential. We can define it in the same way that we defined the gravitational field, which is going to be the potential energy divided by the source of the gravitational force. Here we have something similar, okay? But instead of dividing by the mass, is going to be divided by the charge Q. The same charge Q that we used to define the electric field, okay? That what we call our test charge, that is positive, it's always positive. Okay, there is one important thing about electrical quantities, okay? It is very difficult to measure an electric field. In practical terms, here you go. In practical terms, it is very difficult to measure an electric field. There are instruments that do that, but they are very expensive. However, when it comes to the electric potential, we have something completely different, okay? It is much easier to measure this quantity we call the electric potential. And remember, the electric potential, which is related to the electric potential energy. So there is this relationship between the electric potential energy and the electric potential. Okay. Having said that, and and the way to measure an electric potential is, there are all sorts of devices there that we can buy. You do that with a voltmeter. Okay, the electric potential is measured. Here you go. I'm going to put the units for each of them, right? The unit for the electric force is, now let's put another, here you go, units. Okay, the units for electric, for the force, you already know. Okay, and that's going to be the Newton. Whether it is a gravitational force or an electric force, the unit for the force. Here you go. Someone else is coming. Let me hear. Okay. Shift cell to the left. Cancel. Good. In the case of the electric field, oh gosh. Okay. No, I don't want to do that. I got it. Yeah, now I got it. In the case of the gravitational field, the unit you already know what that is. One is going to be meters per second square. Okay. And the other is going to be Newton per Coulomb. That's the unit. That's the unit for electric field. For the electric field, okay. All you can, there's no much secret about this unit, right? All you have to do is to do dimensional analysis here. In the case of the potential energy, it doesn't matter if it is gravitational quantity or electrical quantity, the unit is going to be joules for both of them. And what changes here is going to be the case for electric potential. Okay, for the gravitational case, the unit of gravitational potential, you can see that is going to be joules divided by kilograms. In the case for the electric field, the electric potential is going to be joules divided by Coulomb. Okay, but now this quantity that you see right here appears so frequently in physics that we give it a name. We call it, you have most likely you have already heard of this unit. We call it volts, and abbreviated by the letter V. Okay. So we do have ways of measuring the electric field here. We do have ways of, but those instruments, they're very expensive. You are better off trying to measure the electric potential, which can be done with very inexpensive devices out there. I have one right here in my hand. I have bought one of those devices for like $15 in the past. Okay, and it was not a bad one, it was a pretty good one. Okay, I'm going to show you one here. Let me stop sharing so you can see what I have here in my hand. Oh, let me. Good. Is a device called a multimeter. Okay, I do not know, maybe some of you have already played with something like that. There are all sorts of multimeters out there. We call it multimeter because it can measure several things. One of them is voltage. So what you have here inside is a voltmeter. That's the type of device that we use in this experiment. I'm going to give you a demonstration how this device works. But first, let me show you all sorts of different voltmeters that I sold out there in the market. Multimeter, okay. Okay, I'm going to share my screen with you. Here you go. If you go in Google, you type multimeter. Okay, you're going to see all sorts of multimeters out there. Their price range, can be, you can have very cheap ones and you can have very expensive ones, okay? This one here is listed in terms of Brazilian reais, right? And it costs $1 is like 5 reais. So this one costs $5 only. I'm surprised. I have never seen a multimeter that costs so little. Okay, $5 multimeter. This one here. Okay, this one here you can see is 10 times more expensive, right? Because so it should cost around $50. But then you have expensive multimeters as well, like this one here. This one must cost what? Must cost around $1,000. I suspect. I estimate. Let's see. Let's see. Oh, taking too long. Oh yeah. Oh yeah. $1,500. This one here. So you have this huge range of prices for multimeters out there. Okay. And that and just for the fact that you can buy a multimeter that can measure voltage for, let's say, $5, like this model that you have right here, it shows, it's a testament that measuring voltage is far easier than to measure the electric field. Some time ago, I ended up buying a device that measured the electric field, but it was like $5,000. I bought that for my lab. Okay. So here you go. That's what you have. Can you remember that? Electric potential is associated with potential energy by the same token that the electric field is associated with electric force. In both cases, the field and the potential, in order to obtain the field and the potential, you must divide the previous quantity, their related quantity, by the charge itself. In the case of the field, you divide the force by the charge. In the case of the potential, you divide the potential energy by the charge as well. Okay? So don't forget, voltage is nothing but a measure of energy. The measure of energy. What else do we have to know? Remember, in practical terms, it's very difficult to measure an electric field. However, it's much easier to measure. It's much easier to measure the electric potential, which is related to the electric potential energy. The device it's much cheaper. The device to measure electric potential or voltage is much cheaper. Can be as cheap as $5. I am surprised, I never saw a $5 multimeter there in the United States, but we do have those here, those in Brazil. 27, almost 28, a little bit more than $5. Amazon.com. Okay, what else do we have to know? Okay. You have to know about the types of field and the types of field that we have out there. Okay. So let me get another. There are two types of field that you have to worry the most. Okay. You have to worry about for this course, right? You have. What's going on here? Okay, good. So you have to worry about a uniform field and you have to worry about the field of a point source. Let me paste that for you. Okay. In the case of a uniform field, it's just like the gravitational field that we find nearby the surface of the Earth. The value of G is downwards 10 meters per second squared. We can also produce a uniform electric field. Okay, it is also possible to produce a uniform electric field. We didn't get to that yet, but we're going to get to that next time. Okay. If I were to illustrate an electric uniform gravitational field, let me get that for you. Go. It's going to be just something. Let's see. I'm gonna get down up in here. No. Oh yeah, here you go. If you want to illustrate a uniform gravitational field, all you have to do is to illustrate something like that, in which you have arrows pointing in the same direction and with the same length everywhere. What we are saying here, we are saying here that at this point in space, the acceleration of gravity or the gravitational field is 10 meters per second square, right? At this point as well, at this point as well, and so on. Okay. And it's possible to generate something like that with an electric field as well. How do you generate something like that with an electric field? Okay, the way to do that is not simple, but the geometry is rather simple. Okay, so here you go. The analogous of a uniform electric field is that of a very large plate that is uniformly charged. All those arrows that you see here in blue are arrows for the electric field. Okay, and the field ends up being uniform. Okay, and so what we so we have a uniform gravitational field, a uniform gravitational field, a uniform gravitational field is the one that we experience nearby the Earth's surface. Okay. On the other hand, a uniform electrical field is the one that's generated. That is generated by a very large plate uniformly charged. Okay. In this illustration here, again, the field is going to be to the right for a positively charged plate. It's going to point to the right, and on the other side is going to point to the left, but it's still going to be uniform. If the plate were negative, the field would be pointing towards the plate. For positive, the fields point away from the plate. Remember, positive charges, fields point away. Negative charges, fields point towards. Positive charges are sources of electric field. Negative charges are sink of electric field. Okay. In the experiment that we are going to do, what we are going to do, we are going to combine this positive charged plate with this negatively charged plate. Okay. When we do something like that, something interesting happens. When you electrically charge one plate negatively and the other plate positively, something interesting happens. Note, see that this plate here is going to have a field to the right, to the left, right? Here you go. The blue plate is going to generate those electric fields to the left. The electric fields illustrated by the blue arrows. Past the blue plate, the field is going to be to the right, right? Whereas the negatively charged plate is going to generate field that point towards it. Within this value, within this volume, the field of the negative plate is pointing the same direction as the field of the positive plate. You see that? Outside the volume, we have the opposite. The field of the negative plate points contrary to the field of the positive plate. And then we get something like that. No field outside the plates and a uniform field inside the plate. We are going to verify that with this experiment of the electric field, and I'm going to walk you through it, how to do that, okay? So, and but before we go this step, let me make you a demonstration of this voltmeter that I have here, so you can have a picture of how we actually, perform this experiment. I'm going to stop sharing. Okay, so here you go. I'm going to turn on my device. Like I said, there are all sorts of multimeters out there in the market. It's called multimeter because it measures several different parameters. One of them is the voltmeter. Okay. Later on, we're going to talk about measuring resistance as well, and we're going to talk about measuring current, electrical current. This multimeter that I have here in my hand can do this type of measurement. This is very small, fits in the palm of my hand. Okay, so I'm going to turn it on. It's a digital device. Oops. Okay, good. It's adjusted for automatic measurement. And let me press again. And I don't want to do automatic measurement. Instead, I'm going to adjust it to measure just voltage. Notice that we have a V here. We have V here as well, right? Here you go. Yeah, V. Okay. At this very moment, I didn't put any source whatsoever to measure the voltage. Okay. But you have a little bit of a noise going on there, very small measurement. What I'm going to do, I'm going to get a source of energy, electrical energy, a battery, okay, like this one, 1.5 volt battery. And we can measure the voltage of this battery with this device. So if you have a cell phone, for instance, that the battery runs out, you can check if the battery actually is dead by using a device like that, okay? So let's see, I'm gonna try. The way we measure the voltage in the battery is by using the black lead of my multimeter, which is the negative part of my device. We have an accumulation of negative charges here in the black cable, and the red means the positive charge, an accumulation of positive charges here, okay? So the way we do it, we touch the negative polarity of the battery. Notice that every battery has both a negative and positive polarity, okay? Here you go. There is even a positive sign here in the top of my battery. It means that we have an accumulation of positive charges here at the top and negative charges here at the bottom. So I'm going to touch this black probe at the negative side of the battery and the red probe at the positive side of the battery. Right now, I'm reading 1.596 volts, okay? I'm going to show that to you. Let's see if I can get the, it's going to be a little bit difficult to raise this, to show that the measurement of this device while I hold the, let's see if I can get it. Do with two hands what I would need a job that had to be done with four, right? But here you go, I managed to do that. We see 1.596, right? 1.596. Oops. Yeah, Yeah, 1.596. Okay. So that's the type of device that we use to measure voltage. A voltmeter, or in this specific case, I'm using a multimeter that has a voltmeter capability that can measure, a multimeter that can measure volts. Okay, and that's the type of device that we use in this so-called experiment. Okay, any questions about that? Okay, so it was time 9:20. I want to take attendance, and there's a first thing that I want to ask: does everybody have a group for today's activity?
I don't.
Okay, so let's see. Let me get your name. What's your name?
Kaylee Hernandez.
Haley, like that? Hernandez?
Yeah.
Okay. Anybody else doesn't have a group? Okay. Okay, so let me take attendance, Haley, and then I'll try to fit you into a group. In this meantime, if you know anybody in the classroom, in this class, that you would like to join their group, that already has a group and would like to join their group, you may do so. Okay.
You're welcome to join group 3, Kaylee.
Okay. Group
Okay,
number.
perfect. Thank you.
You said group number 3, right?
Yes, sir.
Okay, good. So Kaylee Hernandez. Okay, group number 3 here. Anybody else? Just Kaylee? Now, let's see. I'm going to sort everything. Group number. Now, Kaylee's there. Good. 1, 2, 3, 4. Okay, we have 4 here. That's good. So let's go. Artur Pacheco, are you there? I see Artur Pacheco here. I need you to, oh, here you go. Have some, no, to have 3 in our group, join. Okay, good. Here, good. Thank you, Artur. And Elika, are you there, Elika?
Here.
Thank you. Brianna Valencia. Good, thank you, Brianna. I have 2 screens here, so the screen of my webcam is this one I'm looking at you right now. The other screen here is the screen where is my second screen where I keep all the Zoom images and text messages, right? Justena, are you there? Let's see, Justena. Okay, good. Thank you, Justena. Next one is Ashley Diaz.
I'm here.
Thank you, Ashley. Natalie Espinosa.
Here.
Thank you. Let me do something here. View, freeze panes, and freeze panes. Okay, good. Next, Natalie, right? Natalie is here. And Jeanette. I don't see Jeanette. Okay. Who is, someone is trying to come in. Let's see. Daisy. Okay. Okay, Jeanette's not here. And Randy Bautista.
I'm here.
Okay, thank you, Randy. Group number 3, Noor Assam.
Here.
Thank you, Noor. Kennedy Lindsay.
Yes, sir. I'm here.
Thank you. Kaylee Hernandez
Here.
is here. Okay. Ryan Ong. Okay. Thank you, Ryan. Donia Chavarria.
Here.
Thank you. Henry White.
Here.
Thank you, Henry. Vanessa Bonilli. Okay, thank you, Vanessa. Blanca Hernandez.
Here.
Thank you, Blanca. Joshua Jimenez.
I'm here.
Thank you. Alondra Lima. Let's see, where is Alondra? I don't see Alondra here. We have a Zoom user. Who has this? Who is the Zoom user? By the way. Okay, it's not answering. Okay, Daisy Mariscal. Just came in, right, Daisy? Thank you. Alicia Medina. I don't see Alicia here. Yesenia Montes Rodriguez. Thank you, Yesenia. And Brianna Carey. I don't see Brianna Carey here. Destiny. Well, first, Ashley Ortiz, right? Ashley Ortiz, I don't see her. Destiny, are you there, Destiny? I don't see Destiny either. Next is Levilut. Are you there, Levilut? And then we have this mysterious Zoom user. So 18, okay.
I believe that Zoom user spoke earlier during
Oh,
attendance.
Okay. What's her name?
I don't recall. I'm sorry.
Now. So
It
let's
was
give
me,
what's your name? What's your name, please?
Ashley.
Ashley. Okay. Ashley Diaz, right?
Yes.
Okay, thank you, Ashley. I'm gonna put some music here so I know where. Okay, so 18, we have 18, that's good. This number matches. And what we're going to need now, I'm going to, okay, I need you to do the following. I posted, let me write it down here in the notes as well. I posted two PDF documents in Canvas, okay? That if you go there to Canvas, I want you to download these two documents, labs, okay? Labs, P38 SIGFIG and confidence level. I want you to download that. You're going to need those documents. Okay, to post two PDF documents, P38. I'm going to change the name. It shouldn't be P38. Let me change the name. I didn't have time to do that. Here you go. Should be P07. Let's see. Not here. 07. Huh. Rename it. Okay, good. Now I can do that. P07 SIGFIG. Let's name it P07 SIGFIG. And the other one is confidence level. Let me rename it as well.
Professor, do we have a lab quiz today?
No, there's no quiz today.
Okay, thank you.
Let's see. And can I save that? I couldn't save it. Strange. Well, when you download it, just change the name of this document instead of P37. I cannot change it here for some reason. I tried to rename it, but I couldn't. Oh, here you go. I have got to click here. Okay, now I managed to do that. And this one as well. Rename it. Here you go. Click the check mark. Good. So that's the first thing you have to. Oh, you didn't change this one. Edit. 07. Okay. So please, download those two. My notes, okay. And the other one is confidence level.pdf. Save. Please download both of them. Both of them. Okay. For that student who joined group number 3, don't forget to get the link for your group folder, okay? There is a link for the group folder. Just ask your group mates to give you the link for that. Now, what I want to do, I'm going to upload and I'm going to tell you how to work with that two documents. Here you go. Here's your group number, right? I'm going to upload your spreadsheet. Yeah, let's see here. I want to show you how their data looks like. Everybody's data is going to look just like that, okay? Okay, here I'm going to zoom out. Okay, you have to fill up the units right in here. And then you also have to fill up this table, a total of 4 tables. Okay. So that's groups. I will upload those spreadsheets to your group folder. Want to make sure everything is right here before doing that. And I will help you out along the way. Okay, so here we go. I will also go through the step-by-step procedure, how this experiment is usually performed.
Professor, we can't see your screen.
Yeah, okay, let me start sharing. You didn't miss anything. Let's see, thank you for letting me know. Now you can. Okay, group 1. Let's see. I gotta make a little change here before I upload it for you. The spreadsheet is named P07, L01, and G, your group number. Okay, the Word document must have the same title. Okay. Now, group 1, your spreadsheet is there. Group 2, your spreadsheet is there. Group 3, 4, 5, and 6. Someone joined us? Nope. Okay. What else you have to do? You have to download both of them. Also, download the spreadsheet in your group folder. P07L01 group X, right? 1, 2, 3. We're going to need. Oh wait, I'm going to. Some of you already know how to use the confidence level table, right? But nobody here knows how to use this table here. Okay. And I'll help you out with that. It's 9:37. Let's see. But what this table here is all about is for you to find out how to determine the number of significant figures of your measurement. Okay, that's what this is all about. You do not have the multimeter there with you to see how many significant figures your measurement has, right? Just like this one when I was measuring this one here. And when I was measuring the battery. Let's see. You could see the number of significant figures there in the back of your measurement. But since you do not have the multimeter, I have to provide you with the number of significant figures with the devices that we use there at LA Harbor. See here. Let's see, I can let me stop sharing but I can hardly see the multimeter. Here you go. In this specific measurement, you need steady hands to do this. Okay, 1592, right? In this specific case, for this specific instrument, this measurement has 4 significant figures. 1596, okay? And the measurement that you have in your spreadsheet will have the number of significant figures according to the value that is displayed, that is written down. Okay, I'm going to walk you through on how to find that out. Let's share the screen again. So go ahead, download those 3 documents. Okay, what I want to do, let's do the following, while you download everything and get familiar with the documents. Let's have our break now. Break from 9:40 a.m. to 9:55 a.m. Okay. While you do that, and then we get back to this experiment. I'll see you in. Do you have any questions before you go to the break? Okay, if there's no questions, I'll see you in 15 minutes. Okay, we're back here. I just posted a link for a video of today's lab. Okay, so here you go. If you go there to Canvas, there is links to lab videos. As we go along, I will be posting them one by one. Okay, electric field 1. So if you want to review this, this lab, so-called lab, right? It's only 23 minutes long, okay? And you might want to review that whenever you're preparing your lab report, okay? So as we go along, I'll keep on posting the videos for the other labs as well. It's all there in my YouTube channel. So let's your priority right now is to work on the spreadsheet, okay? So at this point in time, you should have already downloaded all the 3 documents, the 2 PDFs, and the Excel spreadsheet P01L01 group number, XLS, right? XLSX, here you go, XLSX. Let's go through that, and then as we go along, I'll tell you what you should do here with this document, right? Your first priority here in this experiment is to plot graphs. That's what I like to do. Here you go. Let's go here, and spreadsheets coming online. That's good. Everything that you see here is everything. No, wait a minute. No, that's not the one I want. That's another lab. It's lab 7. Here you go. Everything that you see here is raw data. Everything that you see here. This data was measured with my voltmeter, with the voltmeter that we have there at the college. This data here was measured with a ruler, voltmeter, ruler, voltmeter, ruler, voltmeter, ruler, right? And so on. And you have to fill up the units here. But before we do that, let's plot this graph, okay? There's a very neat way of plotting this graph. It's not, but there's a very neat way of plotting this graph, okay? And not everybody knows that. But before we go there, let me walk you through the experiment, okay? Here you go. The experiment, and that's also explained in that video link that I gave to you. The experiment starts with a black piece of paper. That's called a conductivity paper. It's a paper that conducts electricity somewhat, okay? It has for this reason that I like to call it resistivity instead of conductivity paper. This paper is so there. We have a bunch of those papers there in the college. And we use this paper to come up with different experiments for the electric field. And one of the experiments, we use this paper. Here you go. We get this paper, right? And then what do? We paint the surface of the paper with a pen that has an ink that is conductive. It's a metallic ink. Okay, this ink here that we paint the paper with. Unfortunately, I don't have this paper right now with me to show you. You know, it's really nice to look to see how it looks like. Okay, so the paint here has flakes of nickel and silver. Okay, that makes the ink very conductive, and that being far more conductive than the paper itself. So we paint this electrode here on this spot, and then another electrode here on the other spot at a given distance. Why are we doing that? There's a reason why we're doing that, right? Remember what I told you about the plates, right? Very large plates like that, they do whenever you charge the plate, they do generate a uniform electric field. And that's what we're going to do with that conductivity paper that you have here, conductivity or resistive paper, okay? That's what you're going to do. We're just going to simulate how two electrodes with this geometrical configuration creates a uniform electric field here, and you're going to see that with the data points, okay? So that's what we use. And then, okay, we're gonna put this resistivity paper. Okay, let's put conductivity. The manufacturer like to call it conductivity. I think it's better if you call it resistivity. Over a cork board. Why do we do that? We do that because the cork board is a dielectric material. It's not going to affect our experiment. If you put it over a metal plate, then the metal may affect the measurements that we take with this paper, okay? Insert 4 pins around it. The cork is below here. The paper now is secure on the surface of the cork. Okay, and we're going to insert a metallic pin in one of the electrodes. Remember, this electrode is a metal, behaves like a metal. It's a metallic paint. It's a paint made of chips of metal, silver and nickel. This electrode is far more conductive than this black piece of paper. And then we insert another pin there, another metallic pin. This pin can be anywhere along this electrode. And what do we do next? We're going to use a power supply. A power supply is nothing but a battery, a fancy battery, a battery that you can change the voltage. Everybody's familiar with a battery, but not everybody's familiar with a power supply. Okay, and then what we do, we usually set this power supply to 10 volts and leave it there. Why is that? Well, you're gonna know exactly very soon why you do that. Get the black cable and connect one end to the black jack of the power supply. Okay, so here you go. In this case of this experiment, we connected the black jack of the power supply, which, by the way, has negative charges on it. Remember your battery? Let me get my battery here again. The battery here has one negative polarity. I'm gonna stop sharing momentarily. This battery has a negative polarity here at the bottom and a positive polarity here at the top, so much that it has a positive sign here. It's kind of difficult to see because the plus sign is very small. In the other battery, the plus sign was better visible. But every time that you get one of those batteries, whatever is sticking out is positive, whatever is flat like that is the negative. So the power supply also has a negative side, a negative pole, and a positive pole. What we are doing in this experiment, I'm going to go back sharing the screen. What we are doing in this experiment, we are charging this plate with a negative charges. We're going to get a distribution of negative charges in this electrode, and we're going to charge this other side of the paper with positive charges by connecting it to the positive end of the power supply. Okay, let me show you exactly how it looks like. So for a real life power supply, right? Power supply is here. A real life power supply look just, here you go, looks just like that. It doesn't look anything like my battery, right? Doesn't look anything, but it does the same job. We have all sorts of power supplies here. Okay, and do you see the red connector here? Let me stop sharing. No, I'm sharing the screen. Here you go. Let me click it here. Here you go. See, we have here the red connector that has positive charges at the end here. That's when you turn on the power supply. So we set this power supply to 10 volts in our experiment. This power supply doesn't go to 10 volts. It looks like it goes only to 7.2 volts. Okay, but there are power supplies that go to 10 volts. See that? It looks like this. No, this power supply goes to 15 volts. Okay, here you go. 0 to 15. 1.5, 3.6, 4.8, right? Until 15 volts. And this is the positive end of the power supply. That's the negative end of the power supply. This other one here is a ground, is more for safety purposes. So when we perform this experiment, you connect the negative of the power supply to the left electrode and the red terminal of the power supply to the right electrodes. Okay, that's how a real-life power supply looks like. And now that I connected my electrodes to the power supply, we can we charge the electrodes and you can start performing the experiment. Okay, so what you have right now, you have, since those electrodes were charged, you end up creating an electric field here inside between those two plates. Electric field lines are coming out from the right to the left side. Remember, positive charges are sources of electric field. Negative charges are sink of electric field. The electric field sink on them, right? So here you go. In the experiment, we set up an x-axis. And that's what this one is all about. Bring to front. Here is I labeled the x-axis. When we performed the experiment, I asked my students not to write down the x-axis in the paper because you can damage the paper and won't be able to perform a good experiment. Okay. Now we set also a y-axis at the inner place of the negative electrodes. Okay, and now you can look in your spreadsheet. Remember, we are concentrating here on the spreadsheet, right? Here are the coordinates that I'm talking about, x and y. X and y, the x and y that are taken from that coordinated axis. The measurements that we make there are taken from the coordinate axis with respect to the origin. Okay, and then visualize the imaginary line, horizontal imaginary line here at the top. There's a reason why we do that. Okay, here you go. Here's our power. No, here's my multimeter, not the power supply. That's the multimeter. Now, we have a fancy multimeter there at the college, which does the same job as this one, the one that I showed to you before. Here you go. Here's the multimeter. I'm not going to go through the details. All I'm going to tell you is that we're going to set this multimeter to measure just voltage, just like this one. This multimeter can measure all sorts of quantities. One of them is voltage, another one is resistance, the other one is current. Okay, so this experiment is about to measure the voltage only, which, by the way, is related to the electric field. Remember that I told you it's very difficult to measure an electric field. You require a very expensive instrument. So instead, what do we do in this experiment? We measure voltage, and from the result of the voltage, we figure out how the electric field behaves. Okay. Here you go. Here are the jacks of my multimeter, just like I have for my multimeter here. The jacks of my multimeter are right here at the bottom. One is positive, the other is negative. COM means negative. Input means the positive polarity. So what do we do here? We connect No, black cable to black jack. Black cable, black jack, black cable of the power supply. Okay, black cable of the power supply to the black jack. So this black jack here is being connected here in this, in the same spot that the black cable of the power supply was connected. And then the other end, here you go, red probe to the red jack. Okay, here you go. Now, basically, I'm doing that. Connect right in here and connect right first the negative and then the positive. Oh. Leave the other end of the red probe on the paper. Okay, so it's going to be something. It's going to be something like that. Now I have the black end of the multimeter connected here together with the negative of the power supply. The positive of the power supply is connected here to the right side of these electrodes of this paper. And the red probe of my multimeter, you know, just leave on the surface of the paper for now, you know. Now we are ready to perform the experiment, okay? We're ready to perform the experiment. Touch the red probe to the pin of the left electrode. Okay, when we do that, because this electrode is set at 0 volts, my reading should be 0 volts as well. We didn't start the experiment yet. We're just doing like a check. We're checking out the equipment, make sure it's working properly. And then touch the red probe anywhere along the surface of the red electrode. Let's see, touch the red probe to the pin. Yeah, okay. And then along the surface, you're going to read both 0 here and here. And then you're going to touch the red probe on the pin of the left, the right electrodes. Recall that I set an energy, electric potential difference, or an energy difference per unit of charge equal 10 volts. Because we have 10 volts, your multimeter should be able to read 10 volts as well. Okay, we're doing just a check, like I mentioned. Here you go. Touch the red probe anywhere along the surface. Okay, and now we are starting the actual experiment. We're starting the actual experiment. Okay, the first thing that we do in this experiment is to find out where we have 1 volt along this line. Here is 0 volts. Here is 10 volts. And anywhere in between, you're going to have a progression of 1, 2, 3, 4, 5, 6, 7, 8, and 9 volts. Okay? That's what we're doing. And then what else are we going to do? We find this point. We write down the x coordinate of this point and write down the y coordinate of this x point, of this point. That's what you have right here, 1 volt, you know, and so on. It's not going to be exactly 1 volt. Okay, you can have values that are slightly close to 1 volt because you're performing an experiment. And here are the position of your point, x and y position, right? Don't forget we are using a ruler. 1, 2, 3. Okay, I'm going to emphasize here in my notes. Okay, we are using the multimeter to measure voltage. P07 sigfig.pdf for the significant figures of a given measurement. We're using 1, step by step here. 1, the multimeter to measure voltage, and 2, the ruler to measure the position of your point. In this case, don't forget, I'm using a resolution, just like we did for physics 6, of 0.001 meter, right? So you have to go only when you write down your significant figures, you have to go only up to the third decimal place. Okay. And you go. Then what else do you do? Record the X and Y coordinate in your spreadsheet, right? Record the voltage read from your DMM in your spreadsheet. And how do we find out what's the right number of decimal places? You go back to your P38 significance figures. Okay, here you go. Number of significance figures. See, we're not using resistance. We're not. You have a bunch of tables in this document. Here is the resistance, right? Measurement of resistance with the multimeter that we are using. But we're not measuring resistance. We are measuring voltage. Here's the number of significant figures for the power supply. Between 0.1 volts and 0.99 volts, the power supply provides you with two significant figures. Between 1 and 9.99, 3, 10, and 20, 4. But we are not interested on this one. We are interested in this one here. Voltage of the meter, of the digital multimeter. DMM stands for digital multimeter. Okay, so if we are measuring slightly less than 1, if we're measuring slightly less than 1 volt, like it happened in one of the measurements below, then you're going to end up having 5 significant figures. If you are measuring slightly more than 1 volt, then you're going to have 5 significant figures as well. All depends on the value of your voltage, okay? If your voltage is between these two values, you're going to have only 1 significant figure. If the voltage is between those two values, you're going to have 2 significant figures, and so on, okay? So that's how you use this table. For this experiment, you use this table here of the voltage of the DMM. DMM stands for digital multimeter. DMM stands for digital multimeter, which can measure, is multimeter because it measures voltage, resistance, current, frequency. I believe that's all they measure. Maybe in certain cases you can measure capacitance, etc. But you are interested only in voltage here at this point in time. Okay, and now you go ahead and repeat for 3 volts along the same axis, the x-axis. You find a point along the x-axis that has 1 volt, then you find a point along the x-axis that measures 3 volts. Measure X and Y and repeat for 5, 7, and 9. Don't forget, here is 1, here is 0 volts, here is 1 volt. Somewhere between those 2 points is going to be 2 volts. Here is 3, 5, 7, 9, and 10. Somewhere between those 2 points is going to be 8 volts, 6 volts, 4 volts, and so on. So I got what you see right here is exactly the following data points. It's going to be those data points here. 1, 3, 5, 7, 9. Okay. Note, see that the Y value is 0, right? Because we're measuring along the x-axis. And then you do for the other positions. I usually like, no, not this one here, this one here, this one here. I usually like to make 6 measurements. We're going to measure where the voltage is, and from those measurements, we'll figure out, we'll deduce what's going to be the electric field. characteristic picture. What's going to be the picture of the electric field? Okay, so next. Now we are going to collect the points exactly here along this line, this imaginary line. Determine the coordinates of the points at 1 volt, 3 volt, 5 volt again, right? But now the coordinates are going to be different for y, right? So here you go. And that's what you have. It's going to be something like that. So we have a point of 1 volt here, another point of 1 volt right here. 3 volts here, 3 volts here, 5, 7, 9. What else? I want to collect total 6 points of 1 volt, 6 points of 3 volts, and so on. Okay, so next we collect points outside this region of my electrodes. Okay, which is not going to lay in the same line as this other one. And do 1, 3, 5, 7, and 9. And then you fill up. You 1, 2, 3, you get 3 more points here in between those two. Okay, that's how we perform the experiment. Just by using the probe of the multimeter. That's how this data was collected. Any questions? 10, 20. I want to make sure that everybody got the spreadsheet. Everybody got the spreadsheet? Let's see. Let's go one by one here. So lab 2, right? Or meeting 2. Here we go. Spreadsheet. Pacheco, did you get the spreadsheet? Yes, good. Should have done that before, right? Let's see. Elika, did you get the spreadsheet? Not just
Yes,
the
I did.
spreadsheet. Huh? You did, right?
Yeah.
Good. Not just a spreadsheet, but the other 2 documents as well, right? The PDF.
Yeah,
as
I
well.
got those too. Yes.
Good. Brianna? Good. Justena, you get the spreadsheet and the other 2 documents? Yes, good. Thank you, Stena. And 2 documents instead of spreadsheet, let's put documents. Documents. Let's see. Ashley, did you get the documents? Ashley, did you download them?
Yeah, I did.
Good, thank you. Let's go for another student here. Randy, did you get the documents? You download the documents? Looks like, are you there, Randy? Let's see here. Randy. Yeah, Randy is present here in my list, but he's not answering. So I'm going to put a star here in his attendance. Okay, let's go for the next one, group number 4. Ryan, did you get the documents, Ryan?
Yeah, I have all the documents.
Okay, thank you. Let's see, another one here. Joshua, group number 5. Did you get the documents, Joshua?
Yes, I got the document.
Thank you. One more. Let's see. Yesenia, did you get the documents, Yesenia? Just type there in the screen if you want. I'm here. Okay, Janet, you're here, right? Okay. Yes, okay, thank you.
Professor?
Yeah.
Hi, sorry. I think that Randy was having some sort of mic issue. This is Kennedy from group 3.
Okay.
But we have the spreadsheet in our Google Doc.
Okay, so ask Randy to type there in the chat box, okay?
Okay, gotcha. Thank you.
Okay. Okay, so your name, you're Kenny, right? Kennedy, right?
Yes, sir.
Okay, let me put yes here. And Janet. Okay, which group are you with, Janet? Janet Garcia, group number 2, right? Okay. Thank you. Put attendance here. Did you got the documents, right, Janet? Okay, thank you. Good. So, okay, and what we have to do now, we have to plot this data. And I'm going to show you a very nice way of getting exactly what you see here in my slide, okay? Repeat for the other voltage, right? So walk with me, okay? Walk with me. The way, not everybody knows how to do that, okay? The way we are going to do is in the following way, step by step. Let's keep on going here. Highlight the first X and Y. Don't highlight the voltage, okay? Don't highlight the voltage. Go ahead, everybody does that, please. Okay, ready? Insert, go to charts, scatter plot. Let me get a little bit of my water. Okay, here you go. Scatter plot and plot it. Okay, you're gonna get something like that. Don't desperate. Don't feel desperate about that. Okay. Notice that those measurements are very close to one another. Okay, it's not that bad because this very close and gives you the impression that the points are at random. So now we're gonna go for the next one. Let's see here what's going on. Yeah. So what you're gonna do next? You're gonna click one of the points. Everything is gonna be highlighted. That's an important step that I haven't shown that to you before, okay? Right clicking one of the points and select data. Here you go. Okay. What you're going to do right now, you have plotted series 1, X and Y. What you're going to do, you're going to add another set of data. I'll call this set of data 3 volts. Series 1 is going to be 1 volt, right? X value, what they're going to do, they're going to highlight the X value here. Let's see, 14, good. And then erase this guy here. There's a little bit of junk in there. I do not know why they have that in there. And then you highlight Y. Okay. And now you click OK. If you got, oh, let's see. Oh, by the way, I want to make it look nicer. So I'm going to edit this first series of points and write that down, 1 volt.
I'm sorry, Professor. Can you do that one more time, please?
Sure. Okay, notice that this group of students, they didn't get a good data points here. They're very close to each other, those 1 volts. They should have extended a little bit more, okay? So let's do that again from this scratch. I'm going to erase my graph, right? Go. The new way of using Excel, what we're doing here. You're going to highlight X and Y. What you're going to do, you're going to plot X and Y. You're going to plot multiple X and Y's in the graph. That's what you're going to do. That's what we're doing. Okay. So insert, right? And plot a regular graph. Plot a regular graph. The secret is not here. Here, everybody has done something like that before, right? The real secret is how to add the other X and Y's to the same graph. That's the secret. Okay, everybody knows how to do that, right? So let's
Right,
go.
and it's just a regular graph, you said, not a scatter plot?
Yeah. It's what I call a regular graph is the scatter plot, right?
Regular scatter plot. Okay.
Yeah. Here you go. Let's see. Insert again. Here you go. Charts, right? Scatter. For me, the scatter plot is the regular graph. I don't like bars. I don't like.
Right. No, I was just making sure. Thank you.
Yeah. Here you go. Now you click one of the data points, highlight them all, right click, and then what you're going to do, you're going to select data. You're going to select data to add data to this plot. That's what select data means. Okay, here you go. Select data. See my series, my first set of data points that I plot. It has a name series 1. I'm going to edit it and call it 1 volt, right? I'm not going to change those. See here the columns, G9 through G14. That's G9, that's G14. The other one is H9 to H14, right? And now that I have my first set of plot of data points here in the graph, I'm going to add 1 more. And I'm going to call that 3 volts. I'm going to select the X values under 3 volts, and I'm going to select the Y values under 3 volts. See the plot, what end up happening? And then you do the same for the rest. Like I said, the students who collect this data, they made the mistake of bunching all those data points in a very small area. They made this mistake instead of here. No, here they spread them out pretty well. Okay, so let's go to the next. Add 1 more.
Okay.
Now it's going to be 5 volts, right?
Professor,
volts.
I have a question.
Yeah.
I'm trying to follow along with this on the on Google spreadsheets. I don't know if we're
Yeah.
supposed to be doing it on Excel specifically or
Yeah.
spreadsheets, but I can't find the function that allows me to add a series.
Yeah,
on-
and Google, Google Sheets, they don't have the same features that Excel has. Okay, so you must have Excel there in your
Mhm.
computer. Okay, in order all the experiments you have to have Excel, because
Okay,
there are some features in Google Sheets that don't have, they didn't implement. There are some
Mhm.
features of Excel that they didn't implement in Google Sheets. Okay.
I see. Okay.
So let's go X value, 5 volts. Everybody's following, Here you go. Okay, another set of points. Now that's 1, 3, 5, right? Click OK, add, right? Next is going to be 7 volts, 1032, we still have time. X. Don't forget this little thing here, this number 1 is just a little junk that they put in there. I never figured out why they did that. They put it in there. Okay. Looks like this group made the same mistake that they made in 1 here, right? Those data points are a little bit compressed. Click OK. That's 1, 3, 5, 7. And the last one, 9 volts. 9 volts. Okay. And click OK here. And I'm done with my graph. Note, see what you see right in here are what we call equipotential curves. Okay, those are curves of same electric potential. Okay, and again, remember, we are not making measurements of electric field intensity. We are making measurements of voltage intensity because the voltage is far easier to measure the voltage than the electric field. Here we have an outlier, a little outlier. Okay, if it were an actual experiment, I'll be asking my students to measure this data point again. It's almost a straight line, okay? Almost a straight line with an interesting effect that we call the edges effect. Most likely the electrode ends around here, if they follow my instructions, right? The electrode ends around here. When you get closer and closer to the edge of the electrode, you do not have a straight line, but it's the equipotential lines start to curve around the edges. It's still a uniform electric field in the bulk of my paper, but at the edges, the fields start to deviate from the uniform field. Okay, so that's the first graph. What else you have to do? We gotta go chart design, right, and do all that things that I mentioned before. Add, did I get it? Let's see, let's try it again. Click it out, click it in. I'm going to add the axis title. Okay, primary horizontal, good. And then primary vertical, axis title. Okay, so you're gonna put X, right? Make it a little bit larger. Between parentheses is gonna be the unit of meters. So we can see better. 10 font is too small. Yeah, you do 12. I usually bold face it, the axis. I usually bold face it. Here's the, oh, what happened to the numbers? It's strange, there's no number here. What happened? Huh, I'm puzzled. It looks like I have to replot my graph. Let me see, axis, primary horizontal. Okay, I accidentally erased the axis. Okay, accidentally, but now I figured out. Did you see that? If you go right here, add chart element, if you click in the wrong place, you're going to erase the X axis. Same thing here in the Y axis, right? You don't want to do that. You want to go in the axis title, right? And did I get it? Did I get with font 12? Yeah, I got font 12. Oh, actually, we should go larger than that because it's too small for me. Here you go. Right click, font. You know, all folks are going to have to learn Excel one day, you know, earlier or later, because you have to use this software. You need to use software in your job. I want to get this one 12. Here you go. And yeah, good, better now. Okay. You want to put those numbers in regular format, right click, format axis, right? Number. I'll put it in scientific because scientific is difficult to read, right? But then you have to increase the number of decimal places, maybe 2. Let's see. Yeah, 2 is enough. 2 centimeters, 4 centimeters, 6, 8, 10, right? 12 centimeters and so on. Or putting everything in meters. Here you do the same thing. Font 12, make it large enough. Here you go. And my axis, I'm gonna make it size 14. Size 14 and bold face. Size 14, bold faced. So this is real life data points obtained from a real life experiment. Real life graph. What did I do here? Here you go. Okay. What you're going to do next? That's what there are 2 graphs that you have to do. That's the first one. That's the most difficult of all the graphs. Okay?
Professor?
Yeah.
Sorry, for the Y values, you had scientific notation. Would you like us to keep scientific notation for the Y?
No, change it.
Okay.
Yeah, I forgot to change this one. Change to regular format.
Okay, just
And
making sure.
I didn't label it either, right? Notice I didn't label it. So
Right, yeah, so
yeah,
we'll just do the same.
yeah.
Okay, thank you.
Okay. What do you do next? You go, let me do that. You go, not scientific, but regular format, number, put 2 decimal places there. Here you go. You got it. What do you do next? Again, those are the surface of equipotential. Those are the surface of equal potential. All those points have the same potential. Those point line, this line has the same potential. Those other points has a different has the same potential as well. Here is 1, 2, 3, 5, 7, 9, right? What do we have to do next? Okay, so go there. Okay, you have to draw an average line across those points. Okay? Ideally, those lines were supposed to be in the vertical, ideally. But that's what do I mean by ideally? Ideally, it is the case in which those electrodes are infinitely long. Okay? But in real life, we do not have electrodes infinitely long. In real life, we have electrodes that are finite in dimension. So my electric potential my electric potential curves are going to curve around this edge here. That's what we call edge effect of those plates. There are lots of devices that have this configuration, useful devices, okay? And we go next. Okay, so there is, like I told you, there is a relationship between the equipotential and the electric field lines. Okay, the relationship is that the electric field lines, they are perpendicular, not perpendicular, but they are normal, which is almost the same, but not exactly. They are normal to each other. What do I mean by normal to each other? Okay, normal to each other means the electric field lines make an angle of 90 degrees with respect to the tangent of those equipotentials. Okay? So here in the bulk of the electrodes, we're going to have pretty good electric field lines that are going to be horizontal. But when you get here at the edge, you're going to see those edge effects. Okay? Okay. And here you go. Oh, we don't want that here. Where do I have it here? Let me erase it. Oh. Repeat for the other voltage where I did that, right? So what we're doing here, we're just drawing here you go, the equipotential lines. Repeat for the other voltage. Let's see here. Let me erase, determine the coordinate of 3 additional. Okay, repeat for the other voltage. Right in here. We don't even need this graph. Okay, so what we want here, draw the equipotential lines, the equipotential lines. Okay, that's what we want to do. After drawing the equipotential lines, draw the electric field lines. Electric field lines, normal. Draw the electric field lines, normal to the equipotential surface. Equipotential, we call it surfaces, but in reality, for this experiment, if it were a real experiment, right, not just this two-dimensional type of experiment, we end up having curves, not surfaces. Surfaces is slash curves. Okay, do we have one more here? Yeah, we do not need this one. Good. So the electric field. So what do? You know, you are going to plot that in Excel, just like I did. And then figure out a way of drawing your equipotential lines. Okay, try to do in Excel. If you cannot do in Excel, you know, transfer Excel to PowerPoint, for instance, right? And draw your equipotential lines there. Or even, you know, another way is just print it and draw the equipotential lines by hand, print this graph and draw the equipotential lines by hand, and then draw the electric field lines. Those are suggestions that I have. Okay, So Randy is here. Let me get Randy here back in my roster. Good. So 2 documents. Any questions about that? There's one more graph that you have to print, that you have to plot. We're doing just the graph first, right? That's how we do. First we do the graphs, then we worry with the units, then we worry with the significance figures, right? The graphs are more fun to do, right? And remember, all that you see here is raw data. They were all measured with our instruments. This guy was measured with my multimeter, and those other 2 next to each other were measured with the ruler. Okay. So now what I'm going to do, I am going to get the average of the exposition that I measured, and plot right in here. In this case, it's not 2 volts. Okay. In my case, it looks like the double check there what you have. It's supposed to be 1, 3, 5, right? 7 and 9 volts. Make sure you.
Mine says 24689.
Yeah. And what about here? Do you have 2 volts or you have 1 volt here in this
I have
column?
2 volts.
Ah, you
Yes,
have 2
same
volts.
for me,
Okay,
Professor.
okay. Okay. So depend on the spreadsheet that you got, right? You are gonna have either 1, 3, 5, 7, 9, or right? 2, 4, 6. So what do you get again? 2, 4, 6,
8, 9.
8, 9. Okay.
Right.
8, 9.
So
it's okay
we
to
just
have
leave that?
Yeah, it's okay to have. It depends, right? What do you have? Do you have 2, 4, 6, 8, and 9?
Yes.
Okay, so it should be 2, 4, 6, 8, and 9 here.
Okay.
Here, this group of students, they measure 1, 3, 5, right? 7, and 9. So what do we have here? Here we have the average of X, right? Average of X, average of X, average of X, average of X. And then what do I have here? I have the average of V, the average of V, the average of V, average of V. Why am I doing that? Well, am I doing that? Because I'm doing that because I'm going to plot a second graph. I'm going to plot a second graph. What do I know about this type of electric charge configuration, right? What do I know about this type of electric charge? You have negative charges here in this electrode, positive charges in this electrode. What do I know from theory? From theory, I know that the voltage is going to increase linearly. That's what I know from theory. And now that I get real life data, I want to know if my real life data reflects what the theory predicts. Okay? And because of that, I took the average of the voltage and I took the average of the position for each equipotential line. Let's see if it's a linear function or not. Here you go. I'm going to plot this as a scattered plot, chart, scattered. Here you go. Wow, it looks just like a straight line, right? Again, go ahead, change your format of the axis. And then what else do you do? You're going to plot, you're going to go to add trend line. Let's see what's the equation for this. Okay, for this line, that's the equation of this line. And look at the R square. The R square is very high. The confidence level is going to be high for this graph. Everybody did that? So 2 graphs, right? Let's see. 1049. Let's go a little bit. Let's see if we can go 5 or 10 minutes. Right? I'm going to explain what that means to you all. You don't always get a straight line for different configurations. This configuration, this is a specific configuration. Yes, you do get, but other electrode configurations you don't get. You don't get a straight line. Okay. Here you go. this specific configuration, yes, you should get close to a straight line. But then there is this other, let me show you another one that we're gonna do next time. We don't get a straight line because of electric charge distribution. This one, see, that's the second one, okay? Oh, man, I did something here. I was not supposed to do. Here you go. Let me see, I can open it. Yeah. Cover. Where is that? Browse. Oops. Yeah, I want this one here. One more student coming. Yeah, let's see. See, we are going to do a different configuration like this one. Okay. Electrodes centered around a circumference. Okay. In this case, you're not going to get a straight line when you plot V against the distance from the center. That's because you have a different charge distribution here. Okay. Going back here. And let's see, 2 graphs, right? I want you to plot 2 graphs, and I'm gonna call graphs. Let's see here. I'm gonna give a little break to the group number. Oh, wait a minute. It's supposed to be 1, right? Oh no, it's supposed to be 2. Okay, one more student coming. Jeanette. Alondra, are you there, Alondra? I think I saw Alondra joining us. Are you there, Alondra? Oh, label, okay. Label, is label there? I think I saw.
Yes, I'm here, Professor.
Okay.
Professor, I am here. It's Alondra here.
Label, you do not have a group.
No, I don't have it. But I can work alone. I don't have any problem with that.
Okay, you joined us very late. Okay, you shouldn't be doing that. Okay, so and we have to set up a group folder for you as well. I'm going to give you attendance this time, but next time I want you to be here on time. Okay.
Yes, sorry for being late. It's just my computer was not ready. Thank you.
Okay, so let me see here. Let me go from each. Okay, I'm gonna give a little break to group number 1, right? Let's see. Natalie, did you get the 2 graphs?
Yes.
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 Have any questions about how to plot them?
No.
Okay,
no
good.
questions.
Noor, did you get the 2 graphs?
Yeah, I have.
Okay, any questions?
No, all good.
Okay. Next one here, Donia, did you get the 2 graphs?
Not yet, but I'm working on it.
Okay, working. Okay, let's see. Vanessa, did you get the 2 graphs? Vanessa there. Vanessa Bonilla, she's there.
Is this for group 5?
Yeah,
group
that's for group 5. We're working on it, Professor, right now.
working. Okay.
I have a quick question just about the first one. What do you call it? We're busy fixing the Excel while I explained it. Do you mind explaining real quick how to get the first plot again?
Okay, let's do that again.
Appreciate it.
Let me finish first here. Which group are you with?
Well, I'm group number 5.
5, group number 5. You are Joshua. Okay.
Yes, sir.
Okay,
Thank you.
good. So let me finish here with group 6 and we'll do that again. Okay. Daisy, did you get the 2 graphs, Daisy?
Yes, I got the 2 graphs.
Okay. Alondra is not here. So, oh yeah, Alondra is here, but she's not answering. Oh, here you go. Yeah, okay, Alondra, make sure. Yeah, make sure you don't come late again. Okay, I'm gonna put a
I had
little.
some issues with my Wi-Fi. I'm sorry.
Okay, I'm gonna put a little star here. Late. Let's see, late. And Alondra, you are in group 6. Okay, so Leibniz, right? Leibniz, let's see what we're gonna do here. While you all working on that, I'm gonna create a group for you, a group folder for you, okay, Leibniz?
Okay, yes.
And we'll upload, here you go. Let's see. Okay, good. Now I'm gonna create here share. Restricted, and the link. Viewer editor, copy the link. Okay. Yeah. Link for group 7. Here you go, Label. You have a link there for group 7. I'm going to upload your spreadsheet now. One. Good, the spreadsheets in there. And label, I'll put it group 7. Good. And the question now is, let me take notes here, P07. So plot 2 graphs, 1, right? Equipotential, curved, slash line, and 2. The average versus X average. 2 graphs. Subscript. Okay. Oh, let's see here. For graph 2, right? Obtain the regression equation and the determination coefficient. Okay, determination coefficient again is R squared. Obtain. Now I want you to look at the slope of this graph, okay? In my case, of the of the second graph, right? Of the second graph. In my case, what is the slope? In my case, the slope is 50. Okay, but it's not just 50 out there, remember? Okay, you must know what the unit are, what the unit of this slope is as well, right? Okay, the unit of the slope is the slope of the vertical axis divided by the slope of the horizontal axis. Okay, so the unit of this slope is going to be 50,008 volts per meter. Okay, 50.008 volts per meter. That's what the unit is. What does it represent? Okay. What does it represent? Well, let's go back to my thing here. Potential, electric potential. Remember that electric potential has units of joules per coulomb, right? Volts, joules per coulomb. Let's see here. And my electric field has units of Newton per coulomb. Okay. So let's write that down. Here you go. You're gonna see exactly what that means. Okay, so here you go. Volts per meter is in reality joules per coulomb, right? Joules per coulomb divided by meter, like that. And then if you go back in physics, mechanics, right? Physics 6, you're going to remember that joules is what? Is Newton times meter. Make sense? Right? I'm going to do the math here for you. I'm going to do the math in a better way. I don't like to use it. Here you go. The slope is equal to 50.008 joules per coulomb. And by the way, wait a minute, let's put it volts per meter. Here you go, volts per meter. And by the way, volts is what is joules per coulomb. Joules per coulomb, like that, which can be here written as meter coulomb. Joules divided by meter coulomb. But remember from physics 6 that joules can also be here written as Newton times meter. And look what we get. We get a unit that's Newton divided by coulomb, which, by the way, is the unit of electric field. Okay? Newton per coulomb is the unit of electric field. So that slope, consequently, the slope that you obtained in the graph is in reality the value of the electric field between these two electrodes. Okay. So that's how we get the electric field. Not only we get the direction of the electric field, but we also got the intensity of the electric field. In my case, it was 50 newtons per coulomb. In your case, maybe it's going to be different, or maybe it's going to be close. Electrodes, is 11:05 right now. And any questions? So we plotted the graphs. Okay. And we also got the intensity and the direction of the electric field. Okay. So now we're going to have a little break, and then we can finish the rest when we're back. Right now is 11:06. If you do not have any questions, we can go for our break. That's 11:21. Okay. Break from 11:06 to 11:21. Okay, see you in 15 minutes. I'm gonna pause the recording and then please remind me to turn on the recording again when I come back. Okay, good. Oops. Okay, so we plotted the two graphs, and we also got the intensity and the direction of the electric field. Such a simple experiment with a device like that, we can use to find the electric fields of different charge distributions. Okay, and now what else do you have to do? Okay, 1, plot the graphs. 2, find the slope, which is the electric field intensity. And now I want you to work on the units and work in the sig figs, significant figures. Right? So remember, we are using only the main units of SI, only the main units of SI. Okay, which are meter, kilogram, second, mole. I have them memorized already. Mole, the other one is coulomb, right? Candela. Oh yeah, Kelvin. Kelvin should come before mole. 1, 2, 3, 4, 5, 6, 7. Okay. Working in the units. Report them only the main units of SI or their report them in the main units of SI or their combination. Okay. Let's see. Let's put this way. Main units of SI, comma, or their combination. working the significant figures as well. So graphs. So let's see. Let me help you. Yeah, I'm going to erase my graphs because I don't want them here. Okay. Okay, so here, you already have the units for everything here that's in blank. Okay. What you have here is going to be just a repetition of that. Just copy and paste them here, so you can get a good grade, right? And here, if you take the average of X, what's going to be the unit of the average of X? If you take the average of the voltage, what's going to be the unit of the average of voltage? In these 3 columns, okay, this is a little bit more difficult. This is a little bit more difficult. You have to know the equation, okay, that you are using. What I'm doing here, I'm taking the standard deviation of the X position. Okay, that's what I am doing here. And in order to know the unit that you are working on, you have to know what is the equation for the standard deviation. Once you get the equation for the standard deviation, you perform a dimensional analysis and you find out what's going to be the unit for sigma. Okay, in this case, sigma x is going to be the standard deviation divided by the square root of 6. Why square root of 6? Square root of 6 because you have 6 measurements. Okay. The square root of 6 has no dimension whatsoever, has no unit whatsoever. So whatever the unit that you find for the standard deviation here is going to be the same unit for this guy here, sigma x. That's called the standard deviation from the mean. Okay. So what's the equation for the standard deviation? Let's write that down together. Okay, the equation for the standard deviation is that's the basic statistics, right? The equation for the standard deviation is the following. See, am I recording? Yeah, I'm recording here. Sigma, okay. I'm going to write it down in the easiest possible way first, okay? It's gonna be, x1 minus x average. I'm going to do the following. Instead of x bar, I'm going to put x average like that. And then I'm going to put it in short. If you took a statistic, you should know that, right? And plus 1, 2, 3. Oh, by the way, it should be a square here. Should be a square here. In this case, we have 6 data points, so it should go from 1 to 6. Okay, what else? What else? Yeah, let's look at there's more, a little bit more here. Standard deviation. Standard deviation equation, right? The equation formula, yeah. No. Here you go. Divided by n. In this case, should be If n would be 6, and everything here is a square root. Okay. Here you go. And then we also have a standard deviation from the mean. Let's see. That's standard deviation. That's not a standard deviation from the mean. Well, I'm going to tell you. Okay. I'm going to come up with the shorthand of this equation. Here you go, summation. Oh. Here you go. Xi, I going from 1 to n, right? In this case, n is equal to 6. In our case, n is equal to 6. And I have to divide by n as well. And everything is in a square root. Oh. Here you go. Thunderstorm. Okay, everything here is a square root. If you do dimensional analysis of that, of this equation, x has units of meter, x average has units of meter, n has no unit whatsoever, the unitless quantity. Meter gets squared. Okay, so when you sum all of that, you still get meter squared. Take the square root of meter square, you get meter. So the standard deviation of your quantity there is the unit of the standard deviation of your quantity there. Now it's going to be meter. Okay. Let's see, the standard deviation from the mean. You know, depending on the equation that you see out there, they usually make it also any -1. Okay, I have seen different definitions of the standard deviation. You know, but whatever, you know, whatever we have in there, Excel, you know. Excel is calculating for us. What about the standard deviation from the mean? Do we hear the, by the way, do we hear the thunderstorms here? Sometimes I get scared of those thunderstorms. Let's see, standard deviation from the mean. Standard deviation from the mean is not much different. It's just sigma divided by square root of n. Let's see. Deviation, it's to yeah, it doesn't look like they have it here, but anyway. Okay, it's going to be standard deviation from the mean. What's the notation that I use there? Sigma sub x. Okay, it's going to sigma sub x is going to be sigma divided by square root of n. Square root of n. Okay, so you can see that the unit of sigma sub x is going to be the same as the unit of sigma. And then we have the last one. The last one here is sigma x over x average. Right? We already know that the unit of sigma is meter, the unit of sigma x is meter as well. So what you're going to have in the unit here is unit of meter divided by meter. Meter cancels meter, and then you get a unitless unit. Okay? That's what you get for that. And there's no need to, remember, there's no need to come up with the significant figures of those parameters, but everything else you need is significant figures, right? Everything else you need, you're going to need the significant figures. And then you have to do the number of data points, fill that up. It's going to be 6. The regression equation. There's something wrong here with this guy. Interesting. Okay, merge. Okay, it has to be merged. Okay, it has to be merged for some reason. It merged by itself. And then you put the values. 6, the equation, the regression equation, and the confidence level that you know, right? The confidence level you get from that confidence level table. If you 1136 here, and finally the unit of the slope, you write down the electric field here and the numerical value of the electric field. Unit of the slope and the electric field, the value of the slope and the value of the electric field. Okay. And by the way, let me just clarify what I meant about the slope is the same as the electric field is the same as the slope. It's not the same. Okay, there's a slight difference. Okay, when the slope that you're obtaining in the graph is in reality the value of the electric field, the magnitude of the electric field. Okay, in reality, the relationship between the slope and the electric field is like that: the slope minus the electric field. Okay, so if you go back to that graph that you saw in my notes, see that the voltage is increasing from the left to the right, right? And yet the electric field is pointing from the right to the left. That's what this negative is all about. That's how we define the electric field. The electric field is minus the variation of the voltage with the distance. If you were to write that down, here you go. E is minus delta V over delta, in this case Lx, right? In our case, it's one-dimensional type of problem, so it's going to be something like that. So the slope you get ends up being equal to minus E, okay, which is equal to minus the slope. $11.39. We're starting to have a thunderstorm here. Any questions? 11:40:39. Okay. I am logged into my cell phone here in case electricity goes out. In case we have a blackout here, I will stay with my cell phone. It's fully charged. No problem. Any questions? Let's see.
Professor?
Yeah.
Yeah, so everything you did just now in this session, or at least regarding the lab, was covered in that video as well?
Yes.
Okay, awesome. Thank you.
Yeah, just keep in mind that, let's see, some of you don't know how to find the confidence level, right? Because you didn't take physics 6 with me. Is that
Right.
Yeah, okay, so let us cover that quickly.
Thank you.
here. Okay, and confidence level. But in case that you need confidence level, let's go back to that table. Confidence level must be my download. Yeah, here you go. Here you go. Okay, so here you go, confidence level. And then I will walk you 11.4. Let's do the confidence level first. You know what? Let's do the significant figures first, and then we do the confidence level afterwards, okay? Let's do it this way. So I'm going to give you an idea how to get the right significant digits there. Wow. Let's cross the fingers. We are having a thunderstorm here. Let's cross the fingers, make sure that light doesn't go out. Okay, so let's. Okay, so I'm going to plot this graph again because I'm going to need this data, right? Insert. Here you go. Trend line, display equation on chart, display R square. Here you go. Oh, I'm sorry. We're going to do the significant digits first. Let's do the significant digits first, and then we do the confidence level afterwards. Okay, so it's not that difficult to find that out. Okay, so let's start with the voltage. You have to look at the value of the voltage here. In this case, my voltage is 1, exactly 1. Okay, and according to my table, you must have 5 significant digits. Don't forget that's the table of the voltage of the DMM. The DMM that we use has this specific characteristic. Okay. Different multimeters have different significant digits, but this is a specific one. I went through the trouble to find out how many significant digits that the multimeter had for voltage. So this is a specific multimeter at 1 volt has 5 significant digits. So how do I fix that? Right now I have only 1 significant digit because it is in the scientific format. Okay. So what do? We must have 5 significant digits here. We go to format cell. And in order to display this value with 5 significant digits, here you go. Let's follow. Right now I have 1 digit, right? I'm going to put number, change it to number. Right now I have only 1 significant digit, right? It was initially in a scientific format, but they're going to put it in numeric format. Right now we have only 1 significant digit. I add 1 decimal place. We end up with another significant digit. I add a second place, decimal place. We end up with 3 significant digits, 4, 5. So in order to get 5 significant digits, I have to display this value with 4 decimal places. Okay, if I click OK, now the number is in the proper format. We go here, do the same thing. 1.022 is more than 1. So it's this range. It's supposed to be 5 as well. So we go ahead and put, numeric format and 4 decimal places to result in 5 10 digits. Okay? And so on. That's how you do it for voltage. For the X and Y values, you use the resolution of your multimeter, of your ruler, which it goes up to the millimeter, up to the 3rd decimal place. Okay, and everything here should have the same number of decimal places. Format, don't forget numeric 1, 2, 3. Right? If you're going to measure up to the millimeter, you have to display up to the 3rd decimal place, and so on. Okay. Remember, that's the ruler, and the ruler has 1 millimeter of resolution. So you go ahead and display up to 1 millimeter. I'm going to, return to what we had before. And now, so you can do that for your own data. Now let's take a look at the confidence level. 1146.
Professor?
Yeah.
Sorry. So for the voltage with the significant figures from 6 to 9, at least for the data that I have, we would just use 5 sig figs, right?
From 6 to 9 is between this range. See that?
Oh, okay, my bad.
6 to 9 is
You're right.
within this range. So you read here the table.
Okay, yeah, sorry, I read it wrong. Thank you.
Okay.
I also have a question. For ours, for voltage 2, the very first one, since yours is just 1, when I put the significant figures, it wasn't just 2, it was 2.0670.
Which group is that?
Group 3.
Group 3. Let me get your spreadsheet here. Lab report, raw data. Group 3. Okay, group 3. Oh, no, it's not group 3. Sorry, let me go back here. It's lab 1, group 3, not lab 3, group 1, right? Which value are you talking about?
The very first one, I was just wondering that, yeah, that one, when you change it to the numerical value, should it be just 2, or because I got like a random decimal?
Yeah, it's a 2-step process, right? First thing, you have to change the format of the cell, right? Instead of scientific, you use numeric, right? You did that, right?
Yeah.
Okay, but now you're displaying 2.022. That's all. If I end up here, you're going to get what you're getting there, right? Is that what you got? You got? Hello?
Yeah.
Okay, so you missed something. There's one more thing that you gotta do, okay?
Yeah,
So
I
what-
put 4 sig figs.
2, let's see. Supposed to have 4 significant figures, right? So how do you get 4 significant figures? You add 3 decimals, right?
3 decimal. Okay.
You add 3 decimals to get 4
Yeah,
significant.
I was just wondering if it was supposed to be just 2.000 because yours was 1.00.
No. When you perform the experiment, you never get exactly 2.00.
Okay.
It may happen that you get, but those are like exceptions, right? So whenever you're performing the experiment, you try to get as close as you can to the 2.000.
Mm-hmm.
But if you try to do that, you're gonna take forever to do the experiment. So you get as close as you can.
Okay.
And that's what this group of students did. They got to the 2.067. Okay, so here you go. And the other ones are also different, right? You can see it. Look, you never get exactly the same value. That's a type of data that I believe, never get exactly the same value because it all depends on how you're handling the probe there in the piece of paper and so on. 1150. Okay, one more before we go for the confidence level.
Are we supposed to do that for the second table too, where the X and X average
Yes,
and V average?
that's right. That's right. Don't forget that now you have an average here, right? You have a summation and then you have a division. So you may or may not increase the number of significant digits. If here you have 3 decimal places, here you may have 4 decimal places because you're averaging the value. You may, depending on the value, on the specific value of X, right? When you sum, you know, when you sum those quantities here, you may end up increasing the number of significant digits. So watch out for that. And the same thing applies to the V, right? The same thing applies to the V average. You may end up increasing the number of significant digits here. Let's go for the confidence level now. 10 more minutes to go. I have, let me go back to my graph. This one here. Okay, here you go. R square, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5 only. Oh yeah, we have only 5 data points. It's not 6 because, okay, yeah, here is, okay, so the number of data points here is going to be 5, okay? 1, 2, 3, 4, 5, because we got only 5 equipotentials. Okay, so let's write that down. In my case, an example, confidence level. So here you go. We have 5 data points for our second graph. Okay, and then we have this table here. This table here displays the number of data points in the vertical direction. Okay, you can ignore this one. You can ignore this one. Okay, this one is just n-2. And it also displays the confidence level here in this row. You gotta learn how to read this table. Okay. And what else? And then the bulk of the table, what do you have in the bulk of the table? You have the values of R square. Okay. So the problem that I am posing to you is that given n and R square, what's going to be the confidence level of your experimental result? Okay, that's, I want to write it down here. Confidence level given n R square and the determination coefficient R square. What is the value, or even the range? Okay, what's the value of the confidence level? Confidence level, not confidence interval. They're different. In my case, I have n equal to 5. And now I'm going to give you an example. I'm going to give an example. Suppose, okay, that's not what we got in the experiment. Here you go. N equal to 5. Suppose my R square was exactly this number. Suppose, okay? Suppose, okay? 0.919173. What would have been the confidence level? Suppose you had got that exactly. Rarely you're gonna get anything like that, but suppose you did. Okay. Okay, for n equal to 5 and R squared equal to 9.919173, the confidence level is going to be exactly 0.99, or which is 99%. That's how you read this table, okay? Similarly, if you had gotten an R square of 0.982356, the confidence level was supposed to be 99.9%. an additional 9 here. Similarly, if the confidence level were to be this value here, if the R square would be this value here, your confidence level would end up being 0.95. Okay. Now, in real life, you do not get those values. In real life, you don't get those values. Okay. In real life, you get a number that's somewhere in between the values that you saw. Somewhere in between the value, between those two, or even between, or even less than this one, between those two, blah, 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 and more than this one. Okay, because the confidence level is measured in percentage-wise, the value of the confidence level is anywhere between 0 to 100%, or 0 and 1. Okay, so let's find out the confidence level of my experimental data here. I'm gonna close it. Okay, my R square is 0.994. N is equal to 5. 0.994 is somewhere between those two values. You see that? R square is between those two values. So what does it mean? It means that my confidence level is between those two values, 0.999 and 0.9999. 0.999 is 1 minus 10 to the minus 3. 0.9999 is 1 minus 10 to minus 4. And that's what I want you to put there in your spreadsheet. Okay? So going back here, 1 minus 10 to minus 3. Here you go. The lower boundary, I'm calling the minimum value, right? The lower boundary is going to be 1 minus 10 to minus 3. Okay? And what else do we have to do? You have to put an equal sign here in Excel so he can do the math for you. Just putting 1 minus 10 to minus 3, Excel interprets that as a text. It doesn't interpret that as a number. And I need you to put an equal sign so Excel can do the math and write down the number properly. Okay? Here's the same thing. 1 minus 10 to minus 4, right? If I do like that, I'm going to get 99.99%. So your confidence level is between those values, has a lower bound of 99.9% and 99.99%. That's for my spreadsheet. Okay? That's how you use the table that I gave to you, the confidence level table that I gave to you. Okay, 11:57. Any more questions? By the way, every lab that we're going to do is going to have a table like that. A table like that, okay? You put n equal to 5, put the R square value here, and then find the CL. Every experiment that we do is going to have something like that. Okay, so any more questions? Oh, yeah, go ahead.
I have a question for the first table that is equipotential. We need to do 4 tables there, or?
Are you talking about this table here?
Yeah. That
Well,
one.
actually, it's 1, 2, 3, 4, 5, 7, right? 7 columns, right? See that? You might need, you have to work on that. You gotta copy and paste that into your Word document. Okay.
No, I mean, like, I need to do 5 tables, right? It's not only one table for out 5.
What do you mean by 5 tables? You have this table here, right?
No, I mean, like, the graph, like, I need to do, because it's X and Y. So I don't know, I'm confused on that.
You have to do 2 graphs, right? That
Yes.
you understand, right? 2 graphs.
Yes, 2 graphs.
The first graph, you plot all those values here, right? That's the first graph. The equipotential, the graph of the equipotential, right? The second graph is this one here. Only 2 graphs.
Oh, okay.
Not 5 tables, right?
Okay.
This,
Yeah.
this table that you see here has 5 data points, right? The first graph is gonna have 5 data points, right? No, it's gonna have 6 data points. 1, 2, 3, 4, 5, 6, right? This first one, but this second graph is gonna have only 5 data points, okay?
Okay. Okay. Thank
I
you.
have only 5 data points. So that's the graph that needs to have the R-squared. The other one doesn't need to have the R-squared. This other graph doesn't have the R-squared, doesn't have the regression coefficient, okay? Make sense?
Yes. Yes.
Okay. Anybody else? Okay, so this lab is due the beginning before the start of the next lab, okay, which is going to be next week. And any more questions? I'm going to stop sharing here my screen. And if you wanna, I'm gonna have office hours right now. If you want to stay around for the office hours, I'm gonna be available here. Okay. And we can finish now. Let me. I'm going to stop the recording as well.